stats enthusiast. Welcome back to our series on sampling distributions. We are still in Unit 5 working on the sampling distributions, and today we are going to look at the sampling distribution for a sample mean. If you're new here, I'm Goldie, and I'm going to take you through creating the sampling distribution for a sample mean, as well as talk about possibly the most important theorem in statistics, the central limit theorem. So sit back, relax, and get ready to take notes. Let's dive right in.
Okay, we are introduced to a lot of new symbols in this unit. So I want to take a moment before we get into today's section of notes to go over some of the symbols we've encountered. In this chapter, in this unit, we are dealing with two different types of data. We're dealing with proportions and we're dealing with means. Proportions is for categorical data and means is for quantitative data. And then within each of those, we have parameters and statistics. Parameters describe our population, statistics describe our sample. And then we have a sampling distribution, and we have a mean and standard deviation for the sampling distribution. So for proportions, what we've covered so far is our parameter, our population parameter for proportions is P, and it's P hat for the statistic, what we get from the sample. And then for the sampling distribution mean, it's mu sub P hat, and the standard deviation is sigma sub P hat. So that's what we've worked with so far with our categorical data, proportions. Now for means, we're going to get into this today with our sampling distribution for a sample mean. Our parameter for a mean is going to be mu and sigma because we have population and population mean and population standard deviation. Our statistics are X bar and S, a capital S, lowercase s, but it's S, okay? So X bar and capital S. And then for sampling distribution for the mean and standard deviation, for mean, it's going to be mu sub X bar, and it's sigma sub X bar for the sampling standard deviation, sampling distribution standard deviation. So we're going to want to keep these straight because just the regular mu and regular sigma are parameters. But when you have mu with a subscript of X bar or sigma with a subscript of X bar, we are describing the sampling distribution, which we know is different from the population. So let's make sure we keep that straight as we go through our notes today. So the sampling distribution conditions, two of these are going to be the same conditions that we used for sample proportions, and one of them's different. Okay, let's talk about the two that are the same. Random, okay? As long as the sampling method is random, our mean is an unbiased estimator, okay? So what this will mean, and we'll more formally describe it here in a moment, is that our center for our sampling distribution is going to be equal to our population mean, okay? An unbiased estimator. We had the same thing for proportions. Remember, for proportions, the center of our sampling distribution for proportions was equal to our population parameter. So this is going to be the same for sample means. Now, obviously, sampling method is random. That's when we are actually sampling. If we were to be in an experiment, we would have to make sure we have random assignment. And then the other one is the independent condition. When sampling, we have to make sure the 10% condition is satisfied. So again, that's specifically when we are sampling that 10% condition. So those two are the same for sample means as they were for sample proportions. What's different is the normal condition. In sample proportions, we had our large counts condition that basically told us, okay, if we had enough successes and failures in our sample, then we could say that the sampling distribution was approximately normal. But we don't have proportions anymore, so we have to have a different condition to be able to say that our sampling distribution is normal. Now, if you did the simulation activity for the central limit theorem, you probably already know what I'm going to say here about it. But if you didn't, welcome to the central limit theorem. Okay, the central limit theorem is a key theorem in AP statistics, and it says something really important. It states, we also call it the CLT if you see in there in parentheses, but it states that when a sample size is sufficiently large, okay, so we'll define what that means in a moment, but sufficiently large, a sampling distribution of the mean of a random variable will be approximately normally distributed. And that's a pretty big thing. That says that it does not matter what your population is. Okay, your population could be uniform, it could be bimodal, strongly skewed, with outliers. No matter what your population is, as long as your sample size is sufficiently large, then your sampling distribution will be approximately normal. Okay. And it requires that the sample values are independent of each other, and again, that n is sufficiently large. So independent of each other, that's a little bit out of our control, especially when we are sampling. So for most of the inferences in this class, we just kind of assume that they're going to be independent, that we have a well-designed study. Now, the n is sufficiently large. What does that mean? So we do have a rule of thumb in AP statistics, but in general, sufficiently large, it actually does depend on the population. If your population is already normally distributed, or your population is approximately normal, your n value does not have to be that large in order to satisfy the central limit theorem. If your population is strongly skewed, uniform, bimodal, anything crazy, then your n has to be a bit larger to satisfy the central limit theorem. So instead of being confusing with those different thresholds depending on what your population shape is, we have just a rule of thumb. If your population is normal, so is the sampling distribution of x bar. True no matter what the sample size is. Okay, so if you have a sample size of 10, but you're sampling from a population that's normal or approximately normal even, your sampling distribution will be normal. If the population is not normal, or in a lot of cases it has an unknown shape, we're just not quite sure what it's looking like, the central limit theorem will kick in and tell us that it will be approximately normal as long as n is greater than or equal to 30. And that's going to be our rule of thumb in AP statistics. And for a lot of inferences, it usually is n greater than or equal to 30. In our simulation activity, we saw what happened to the sampling distribution as it got larger. So if you wanted to do that activity or check that out, make sure to take a look. Or you can just trust me, right? N is greater than or equal to 30. That's what we're going to have to check to make sure that we can say our sampling distribution is approximately normal. And always say approximately, okay? Approximately normal. It's never going to be exactly normal. Okay, that's our conditions. Let's kind of summarize this here for shape, center, and spread of a sampling distribution. Because remember, in order to answer questions on the AP exam and for this class, we have to create a sampling distribution. And creating a sampling distribution means that we have to know the shape, center, and spread. So we just got done saying the shape of the sampling distribution for a sample mean will be approximately normal as long as one of these two things is true. If your sample size is less than 30, the population distribution should be normal. Okay? Or you could probably get away with approximately if your population is approximately normal. But if n is greater than or equal to 30, the CLT tells us the sampling distribution will be approximately normal no matter what shape the population is, okay? Or if we don't know the shape. So yeah, we have to check those things in order to cross off that our sampling distribution is approximately normal. For our center, I already kind of spoiled this for you, but the center of our sampling distribution is going to be equal to our population parameter, as long as you randomly selected when you are sampling, or randomly assigned if you're running an experiment. Now the spread. We had a formula for the spread of a sampling distribution for a sample proportion. We have a different formula for our spread for our sample mean. And this is going to depend on the standard deviation of our population. We divide it by the square root of n. So the spread of the sampling distribution still largely depends on your sample size. So you can see here with the relationship of n in the denominator, the larger your sample size is, the smaller the spread of your sampling distribution. Now this is true as long as it satisfies our favorite 10% condition. Only when sampling, but it does have to satisfy the 10% condition to use that formula. And that's going to be your sampling distribution for a sample mean. Okay? Let's get into what the problems look like here. So here's our example problem. We'll go through the 4-step process. It's going to feel very similar to the problems we did for a sample proportion. Ooh, in fact, I see a little typo there. This is the example problems for a sampling distribution of a sample mean, okay? So we are going to suppose that the heights of young women are normally distributed with a mean of 64.5 and a standard deviation of 2.5. What is the probability that the mean height of an SRS of 10 young women is greater than 65 inches? Now, if this sounds familiar, we did a problem similar to this in our first video, except the difference is when we are using a normal probability distribution, we are selecting a single person from our population. When we are selecting a single person or a single thing from our population, we use a normal probability distribution. But you can see here, what we are doing is selecting an SRS of 10 young women. So when we select an SRS of any size, then we create a sampling distribution because we are taking a sample, okay? So step 1, we always want to communicate. So we communicate the parameter in the context of the problem, and then we write down the probability we are trying to find. So the parameter in context of our problem, mu is going to be the average height of a young woman, And then what we are trying to find, that's supposed to be X bar there. It's a little tough to see. But what we are trying to find is the probability that our sample mean is greater than or equal to 65. Okay, so specifically our sample mean there. So that's step 1. We want to communicate. After this, okay, so we got that. After this, we want to create our sampling distribution by finding the center, spread, and the shape. Now, creating our sampling distribution also means we check conditions. So for step 2, you can say create. For step 2, you can also say just conditions if you would like. So our first condition, random. In this case, a random sample was taken. It was an SRS. So we say that the center of our sampling distribution is equal to our population center. So 64.5. For independent, there's a lot going on here, but we check the 10% condition. We check to see if our sample size N, which is 10, is less than 10% of our entire population, which is all young women. Now, this is, of course, a safe assumption to make. There's millions of young women, so we are okay, and we can find the standard deviation of our sampling distribution by using that formula. So that's going to be our sigma, our population standard deviation, divided by the square root of 10, and that gives us 0.791. So you can see the spread of our sampling distribution is smaller than the spread of our population, okay? And that is because when it comes to means are less variable than individual values. So the individual values that make up our population, they vary with a standard deviation of 2.5. When we look at a sampling distribution and we look at our sample means, they are going to vary a lot less from our center. So it's going to have a smaller standard deviation. And normal. Because the population distribution is normally distributed, the sampling distribution will also be normally distributed. Okay? Even though our sample size is less than 30, we can say that our sampling distribution will still be normal because of our population. Okay? So our conditions were checked. We found our center, we found our spread, and we found our shape. So now we can go to step 3, which is going to be calculate. Okay? Calculate the probability by converting your data to a z-score and using technology to find the probability. For a free response question, you definitely want to show your z-score calculation, okay? So this is what we have. Again, those are supposed to be X bars. I'm sorry that it's not showing up that well on the screen. But what we are trying to find is the probability that X bar is greater than or equal to 65, where X bar follows a normal distribution with a mean of 64.5 and a standard deviation of 0.791. So we just found all of that through our conditions. Now we're going to take our 65 and convert it into a z-score. Okay, so we take 65 minus our mean and then divide it by our standard deviation. And that value is going to be 0.632. Okay, so z greater than or equal to 0.632. You can draw your curve and shade the area, which represents the probability that we are trying to find. I always like drawing the curve. And then what we do is we just put this in our calculator. Okay, don't draw the calculator speak, but this is a little snapshot of what you should have in your calculator. Your lower boundary is 0.632. Your upper boundary is positive infinity. Mu is 0, standard deviation is 1. And that's going to give us an area or a probability of 0.2637. Okay. So what you see on the screen is the work you should show for these problems. And then, of course, the last step, once we have all of that, is going to be to conclude. Okay. Conclude the problem. We want to put context to this conclusion. So we would say the probability that the mean height of an SRS of 10 young women is greater than 65 inches is 0.2637. Now we're going to get into our last problem of this video. We are going to look at and compare what we talked about with our normal probability distributions and what we just started solving with our sample means and the sampling distribution. So we're going to look at a particular restaurant that shall remain nameless since we're kind of looking at how much they're undercooking their burgers. Okay, so the restaurant claims that the burgers are cooked to a medium doneness with an average internal temperature of 160 degrees Fahrenheit and a standard deviation of 5 degrees Fahrenheit. So for these questions that follow, we're going to assume that the restaurant's claim is accurate and that the distribution of internal temps follows a normal distribution. Okay, so when we say the restaurant's claim is accurate, we're going to have 160 be our population mean and 5 be our population standard deviation. So A, what is the probability that a single randomly selected burger is cooked to an internal temp of 158 degrees or less? So this question, notice it's a single randomly selected burger. When we are just selecting a single item or a single person from a population, we are working with a normal probability distribution. This does not require a sampling distribution because we are not taking a sample. So to answer this question, again, if you want to make a note, it's not a sampling distribution. You're selecting a single burger. We want to find the probability that X is less than or equal to 158, where X follows a normal distribution, 160 as the mean, 5 degrees as the standard deviation. So we're selecting a single burger. It's a random variable. So that's why it's X less than or equal to 158. And we're selecting it from the population. So we use our population parameters. We convert to a z-score. So we're going to take 158 minus 160 and divide it by 5. And that's going to give us a z-score of negative 0.4. And I'm just going to draw that curve real quick and then shade to the left because we're finding that area. On the calculator, this is what you're going to put into your normal CDF. So your lower boundary is negative infinity, upper boundary is negative 0.4, mu is 0, standard deviation is 1, and we're going to get an area or a probability of 0.3446. Okay. So if I were to answer this in a complete question, if I were to answer this question as a complete sentence, I would say that the probability a single randomly selected burger is cooked to an internal temperature of 158 degrees or less is 0.3446. Okay. So now let's look at B. Okay, so still the same situation with the burgers, but this time a secret shopper comes in at random times throughout the day to test the internal temperature. They select an SRS of 25 burgers and calculate the sample mean. What are the mean and standard deviation of the resulting sampling distribution? So now we are dealing with a sampling distribution because we took an SRS of 25 burgers. So we have a sample. So the center of our sampling distribution is going to be equal to our population parameter, 160. But our standard deviation, we use the formula where we take 5 divided by the square root of 25. So 5 is our population standard deviation, and our n is going to be 25. Square root of 25 is 5. 5 divided by 5 is 1. That's going to be the mean and standard deviation of our sampling distributions. Now, we're not talking about conditions in this problem. It's just asking us some pretty straightforward questions. But in a complete inference problem, you would have to check those conditions as well, and it would satisfy them. So part C, the secret shopper obtains a sample mean of 158 degrees Fahrenheit. What is the probability that a random sample of 25, that shouldn't say cans, that should say burgers, produces a sample mean amount of 158 degrees or less? Okay. And again, assume all conditions are met. In a true inference problem, we would want to check all the conditions and do everything we just did in the problem before this. But let's just focus on finding the probability here. So the probability that x bar is less than or equal to 158. So now we're working with x bar, not x. It's x bar because we are dealing with a sample mean. So we'll still find the z-score. We take 158 minus 160, and this time we divide by our sampling distribution standard deviation, which is 1. This results in a z-score, z less than or equal to -2. So if you draw the curve, it's right there. If you put it into the calculator, -infinity, -2 as your upper, and then you get an area of 0.028. Okay. So why is there a difference? Okay. Why is there a difference in results between A and C? To remind you, this is what we got. In A, the probability that x is less than 158 is 0.3446, and x bar less than or equal to 158 is 0.028. Now, why are they different, and why is one more likely to happen than the other? Okay. So in part A, you're looking at a single burger. Okay. Now, since that distribution has more variability in it, in other words, the population has a standard deviation of 5, which is larger than the sampling distribution standard deviation of 1, you have a higher probability of it happening, okay, due to chance. It goes back to what I was saying earlier in the video, in that single values are more variable than average values. Okay, so that's why having a single burger that's 158 or less, there's just a that's more likely to occur because of the sampling variability, okay, that we've been going over. But in part C, when you look at 25 burgers with an average of 158, averages are less variable than individual values, or they should say, it says have less variability than, instead of are less variability, have less variability than individual values. So we would expect a lower probability of that event occurring just because it has that less variability.
And that wraps up today's lesson on notes for the sampling distribution for a sample mean. Thank you so much for watching, and if you like this video, please click the like button, and you can subscribe to my channel for more AP statistics content. In the next video, we are going to wrap up sampling distributions by talking about the sampling distribution for a difference in sample means. So if you're ready to move on, go ahead and click that link to follow to the next video. And I wish you endless statistical success, and I will see you next time.